Greetings, Earthlings. Well, with this coronavirus thing going around, you can't watch hockey, you can't watch basketball. The only thing left for you to do is watch YouTube videos. So I thought I'd try making a couple just to give you something to while away the hours while you're out or in, not meeting with people, staying away. Social distancing, they call it. Yes, I know all about it. I do it all the time. Forget about the coronavirus. This is my natural state. So I'm going to talk about the state of the Nova 445. I have made some progress here, but I've hit a stumbling block, so that's what we'll look at. So I talked last time about the issue of on the ROMs, the bit ordering, and that I would have to do something to swap the bits around. And what I did is I did that in software, as I mentioned I was probably going to do. But what I actually did is I wrote an assembler in Perl again to generate the code for the ROMs rather than trying to use a cross assembler or some other assembler that's out there. I don't have a Nova, a working Nova right now to run Data General's assembler, so I could run on SimH, I suppose, but then there's the issue of importing or exporting the files from there. So I said, forget that. I'm just going to write an assembler in Perl, and that can generate the hex files for the PROM programmer and do the bit swapping in the right there in the assembler code, in the Perl code. So now I've written this little test program. I had this idea to, since I still, the only I/O device, as it were, is I have a blinky light here, the carry light, which I can blink. So I wrote a program. I thought, well, I'll have it say Nova in Morse code, send out dots and dashes on it, and just continually send Nova in Morse code. And that'll be a good test. That will test RAM as well as ROM. If you remember the previous program, I was just using the registers, so I wasn't actually accessing any RAM. So this one I actually am accessing RAM. Here's the program. Well, and it goes on to the next page there, okay? And it's just a real dumb little program. I have one location in low memory at location 100. Now that's octal again. I remember Nova's kind of an octal machine. And then I have this code which sends dashes and dots. So I have little subroutines to send to blink the light as a dot or a dash, and another one to pause. And so I'm just calling dash dot pause, dash 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 pause, dot 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 pause, dot 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 dash pause, dot dash pause. So dash, let's see, dash dot, that's an N, dash dash dash, dot da da is an O, dit 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 da is V, and dita is an A. And then it'll pause, and loop around. What I'm saying, so now that the code again, at startup, it starts at location 77777. That's over here on this side. That just says jump to Morse, which is a 701, goes back to here. Right there, Morse, and then we'll proceed from there. So that's at 7777. 77700. Okay, So it doesn't give me Morse code. So I've had to hook up the logic analyzer. Now don't worry about this column because I don't have those hooked up. You can see the wires over here. But I don't need them because I can see what's going on, basically, sort of. I mean, not enough to fix it, but okay. So here we see it reading the 77777, and that's S701. So this is just spying on the data bus at the the input clock. So what we'll see on there is both addresses and data. It'll put out an address to to read a memory location, and then you'll see the data coming back. So there's an address 77777, and then here's the data 701. That's what we expect. These are just wait states here. I don't know why there's so many on this one, but okay, 701. That takes it down then to location 77700. That was that jump. That 701 was jump back to 77700. That has a 102440, which is in fact what it's supposed to be. That's a initialize the carry to 1, and then subtract accumulator 0 from itself. That will clear accumulator 0 and clear the carry when that instruction is finished. So 102440. Okay, we proceed then to the next instruction, 77701. That has an 040100, which is again correct. That says store 0 in count, which is this location at in low memory at location 100. Okay, so does the store, and in fact you can see the right. This is actually an inverted signal. So if it's a 1, it's reading. If it's a 0, it's writing it. So you can see it actually write it, and then we see the data 0 that goes out to that location. Okay. Proceeds to 77702, which is the beginning of the loop. That says jump to subroutine dash, which is at 77731. So 77702, 4427, that's correct. And we see it going to 77731, which is where we expect it to be. And this is where it starts to get interesting. That is a 101040, which is correct. And it says move O 0, 0. Well, all that's doing is setting the carry bit to 1. Okay? And then the next instruction that it's supposed to execute is an 010100. Increment and skip if 0 count. Okay? Count is that location in low memory. So it's going to spin in a little loop there, counting up to 65,536. So we go to location 77732, which is that ISZ, and then what do we see there? We see 030100. Now we're expecting 010100, but on the first cycle, 030100, and then it goes to 000100, where it stays, and it reads that as the instruction. Well, that happens to correspond to a jump to that location 100. Location 100 has a 0 in it. 0 on ANOVA means jump to location 0. And I guess 0 has 0 in it because it just stays at location 0 thereafter. So what's going on? I don't know. Oh, by the way, 0, jumping to 0, that's a useful thing to know if you want to zero out everything on ANOVA. This is actually possible. Somebody figured it out many, many years ago. I'll probably do another video just on that. It's possible to zero out all of memory, all of the registers, everything completely on a Nova. I'm not sure that's something you can do on many other processors, but on a Nova you can. So if you want to cover your tracks, you can zero out the whole thing. Again, that'll be another video. But it makes use of the fact that a 0 is a jump to location 0. So what's going on here? I've checked the ROM. And it does have the correct value in it, at least as read by the PROM programmer. But again, here we see, and it's, there's 1, 2, 3 cycles. This ROM rather has access time of about 150 nanoseconds. Each of these clock cycles is 50 nanoseconds, so we're actually giving it about 200 nanoseconds, because there's 3 wait states, plus, the one that it would have if there wasn't a wait state, which is probably not the full 50 nanoseconds, but we're over 150 nanoseconds. But it settles down to a 000100. Again, not sure what that means. I've got more work to do. But that's where it is right now, and I thought maybe people would like to see that, just to know that I'm still working on it. It's still here. I'm not dead yet.